Right, so we're going to demonstrate Medusa capability, hoping to achieve 500 megabits per second with some simple equipment, some tripods, SMs and the Medusa AP.
In order to maximise the sector throughput, PMP 450m uses Cambium Network's cnMedusa technology and its implementation of multi-user MIMO. cnMedusa allows subscriber modules separated by specific angles from the bore site to communicate at the same time in the downlink. SMs meeting this criteria, which requires service at an instance in time, are put in groups. In this diagram, we see two groups of 4 SMs. Each group will communicate sequentially until all SMs requesting data are serviced. In this demo, we will position the 7 SMs so that they will be formed into one group. This allows all 7 to communicate at the same time and will simulate a scenario where all SMs in a sector belong to groups of 7.
What we're going to do now is install the equipment. Initially a rough install, putting the SMs at the desired locations relative to the AP.
In this setup, the centre SM is placed 11 feet or 3.35 metres from the PMP 450m access point. The other 6 SMs are placed at specific distances from the centre SM, as shown in this diagram. This gives the required angular separation between SMs to allow grouping and so spatial multiplexing.
The first one's already powered. We'll power the second, and we normally leave 20 seconds and power them up with a 20-second gap between each one. So we have a page on Medusa which is under statistics and radio, and here we have a parameter called the spatial frequency, or in this case it's the reference SF. Now this is a parameter which effectively tells us where the SM is in relation to the base station. And the base station uses this information such that it can form groups. This is a table here where if the centre SM was on spatial frequency 0, these would be the spatial frequencies required for the other SMs. And if the centre SM isn't quite on 0 and is in 1, 2, 3 or 4 or 5, this table shows you what the values for the other SMs are. So let's go back to the browser, and that was a stroke of luck because the centre SM is already on 0. So if we work down from VC21, which is the centre SM, to VC22, that's 138, where it should actually be 146. For these demos we like to have a lower EIRP just because the SMs are close. So when we set it to 22 dBm, we get 2 new fields come up in the radio configuration page. One of those is called the near field operation. So near field operation, enable near field operation, and then set it to the required distance, which in our case is 11 feet. And the forced channel reassessment allows the continual update of the spatial frequency. We have a spatial frequency on this SM of 138, and we want to move it to become 146. So that's just a small adjustment. Well, that's not quite far enough, that's 140. and we're now on 147, which is close enough. If we get it within plus or minus 3, we're generally quite happy with that. And so the process goes on, adjusting all the remainder of the SMs to the correct spatial frequency as per the table. Just reviewing these, we have the centre at 0, we're looking for 879 there, 733 here and 587 here. On the bottom side we're looking for 146, which is 145, that's close enough, 292, that's fine within 3, and 437, 438. Okay, so before demonstrating the throughput, we just want to disable the forced channel reassessment. So we're going to turn that off, which is back to its normal system operation, where you've got SMs in the field that are generally stationary. So now we can demonstrate our Massive MIMO capability. And we'll initially do that with a link test. So here we are on the link test page, and there's an option at the top to link test with multiple VCs, and this sort of floods all the virtual circuits, all the SMs with data. Currently we have this configuration set for 75%. And we'd be expecting something around 500 megabits per second for this configuration. Obviously with 85% we get a higher throughput, which we can demonstrate. So I'll start the link test. So that's a 10-second link test. And you can see there that we have 492 megabits per second. So we're now going to demonstrate a TCP test and measure the throughput through the system using TCP, and this is with a 75% downlink ratio. The system we've got is we've got a Linux box here where we're just going to do an iPerf test, and we've got 7 Raspberry Pis, each connected to one connected to each of the SMs. We've got a little bash script to send TCP sessions to each SM, and then there's a speed test which is actually measuring the speed on the wire of the SMs. So if we kick that off, and we'll So, right in the top corner here, it's indicating that we're getting 448 megabits per second with TCP. And we can leave that running for, I think it's runs for 100 seconds. And so the radio's now been configured for 85% downlink ratio. So we'll do a link test. Megabits per second. The other thing that the link capacity test shows us is the how the slots are distributed, and it shows by group size. So we've got 7 SMs here, and basically this is showing us that for 100% of the time, all 7 could be put into the same group. So this is where the AP is effectively communicating with all the SMs at the same time and on the same frequency. It might be useful just to show what would happen if we disabled MU-MIMO. Which is a setting again on the link test page. That's the total capacity here is 81, just over 81 megabits per second. So I think that's a pretty clear demonstration of what MU-MIMO is doing for us.
Connecting people, places and things. Cambium Networks.